All right, so we've got example 4 to wrap up this lecture. And we're given that we have a simply supported beam with a uniformly distributed load with a magnitude of W, which is unknown. And we're told that we have a span length of 15 feet. And the cross section, section 1-1, is a 3-inch wide by 6-inch tall rectangle, but the wrinkle here is that the top 3 inches is aluminum, the bottom 3 inches is steel. The aluminum has a modulus of elasticity of around 10,000 ksi. The steel has a modulus of elasticity of around 29,000 ksi. The allowable stress for the aluminum is 15 ksi, and the allowable stress for the steel is 22 ksi. And all that we're asked to find for this problem is the maximum intensity of the distributed load. All right, so fundamental equation, we always want to write that down. I think we have two of them similar to the last problem. We've got the normal stress due to a bending moment. And here we're only going to have bending about one axis. So I'm just going to have negative mz times y divided by iz. The moments of inertia equation, I equals the summation of I naught plus AD squared. That's also going to be valuable. And I'll even put down the transformation factor as well too. N equals E, we'll just say E sub old divided by E new, or maybe, yeah, I think that's fine, or E original, E transformed. Whichever way you want to think about it, it's the original material divided by the modulus of the material that you're replacing it with is what we call our modular ratio. And I think that's all we need. Now, with this in mind, we need to find mz, we need to find y, and we need to find iz. We're basically given what the maximum stress is. So here we have two different stress checks to do. So we'll have to run this equation twice. We'll need to plug in 15 ksi here, find out what the maximum, where the location for the maximum stress in the aluminum is, and make sure that we know what the maximum moment is for that. Go back to the same exact thing, put in the allowable limit for the steel, plug in a y where the steel will see the maximum moment, and then back calculate what W is going to be. So that's what we're going to do. So first thing, I'm just going to focus on the moment first. So in terms of mz, the moment, I need to figure out what is the maximum moment going to be in this beam due to a uniformly distributed load. And this is something you could do drawing the shear and moment diagrams, finding out where the moment is going to be the maximum. So that would be a matter of calculating your reactions. That's going to be WL over 2, WL over 2. Draw your shear diagram. That's going to be a constant linear slope. Draw your moment diagram. It's going to be a parabola that has a maximum at the middle. You can go through the work on your own, but I can tell you that for a uniformly distributed load on a simply supported beam, as a designer, I've done this calculation a million times, and I just know from by heart and from tables that I refer to, the maximum moment due to this type of loading is WL squared over 8. So if I plug in W, I plug in 15 feet for L squared divided by 8, and we get 28.125 times W, and this is going to be in units, assuming that W is in units of kips per feet, this will be in units of kip feet. So this is assuming W is going to be in units of kips per foot. So I could, if I wanted to, and it probably makes sense to turn this into units of kip inches instead of kip feet. So if I just multiply this by 12, I get 337.5 times W. That's going to be in units of kip inches even if W is still given in units of kip feet, kips per foot, excuse me. And that makes sense because we're already given the length here in feet. I think it would make sense to give the allowable load in terms of kips per foot. But then all that we did is we just did a unit conversion to get the moment due to a distributed load like this into kips and inches. So here we've got our moment now. That is what the maximum moment is going to be. It's going to happen at mid-span. That's not necessarily critical, but now we do have something, at least a formula, to plug in for mz down here. So we've got mz, which is great. Now the other two things are going to take a little bit more doing. So y, I guess we could talk about y, but it probably makes sense to do it later. I mean, looking at this cross section, if I have some moment acting on it, the maximum stress in the aluminum is going to be at the extreme fiber of aluminum, which would be the very top of the section. The max stress in the steel is going to be the fiber of steel that has the largest distance from wherever that moment, wherever the neutral axis is, which is going to be the bottom of the section. So I already kind of know where the maximum, what values of y to use for the aluminum and for the steel. It's just going to be the top for the aluminum, the bottom for the steel. Now it's possible, depending on where this neutral axis is, that I might need to look at some other areas as well too, but we'll look at that once we transform the section, which is what we need to do to calculate the moment of inertia about that horizontal z-axis. And this is going to be a little bit tricky. So this is going to be for calculating the moment of inertia. So we can't calculate the moment of inertia of a 3-inch wide by 6-inch tall rectangle because there's two different materials at play here. So we need to transform the section to either turn it completely into aluminum with the same effective stiffness, or turn it into all steel with, again, the same effective stiffness. And so the way that we do that is we choose first which material we want to turn it into, and I'm going to choose to turn this into all aluminum. So I'm going to say aluminum transformed section. So if I'm turning everything into aluminum, where I go from steel to aluminum, I need to multiply the width times some modular ratio. So the top is going to stay the same 3 inches wide by 3 inches tall. That's not going to change. That's still aluminum. But the bottom is no longer going to be 3 inches wide. We need to multiply it into a new effective transformed width. And I'll call that BTR for transformed. It's going to be equal to B original times that modular ratio, which would be 3 inches originally times the modular ratio of the original material, which is steel, which has a modulus of elasticity of 29,000 KSI, divided by the modulus of elasticity of the transformed material, which was aluminum, 10,600 KSI, and I get that the transformed width is going to be equal to, let's calculate this really quick, 8.21 inches. We don't change the height. The height stays the same at 3 inches. So this is my cross section now. It is basically a T-beam, and now this is all aluminum. Original aluminum on top, and then transformed aluminum down below. And just for future reference, that N factor, N is equal to 2.74, because that's going to come in handy later on as well too. Okay, so this is the cross section that we have to deal with for calculating I. And so in order to calculate I, we need to do two different things. We need to calculate the location of the centroid, and that's going to be down below half height because this has more area down below. So our z-axis is going to be somewhere like this, and we care about what is this y bar value. And so to calculate y bar, it is simply equal to the first moment of area. I'm going to measure everything from the bottom, y tilde times A divided by the total area of the cross section. So just think of each of these as having their own cross centroid, as it were. The distance from the bottom to the centroid of this aluminum is going to be the 3 inches plus half the 3 inches is going to be 4.5 inches, and the area of this shape is simply 3 inches by 3 inches. For the bottom shape, it has a centroid at 1.5 inches above the bottom, and an area of 8.21 inches wide times a height of 3 inches. And the total area is just going to be the 3 inches times 3 inches for the top, plus 8.21 inches times 3 inches for the bottom. And for that, we get a location of 2.303 inches. That's measured from the bottom, and that again passes the reasonableness test, because if it was just a regular rectangle, the centroid would be at half height, but here, because we have more area down below half height, it's going to bring that centroid down, and so the overall centroid neutral axis being below half height makes sense. Okay, now once we've got that, now we've got to deal with our moment of inertia equation. Moment of inertia being, it's not a good pen, moment of inertia being summation of I naught plus AD squared. The D distance that we're talking about, this is for the bottom, so I'll call that D2. This is for the top, I'll call that D1. I naught is just 1/12 base times height cubed. A is the area of each individual shape, then D is the distance from the neutral axis to the centroid of each of the shapes. And so if we were to do that here, I'm going to get 1/12, let's do the top one first, 1/12 the width, which is 3 inches, times the height, which is also 3 inches. That'll be cubed. And now the area is 3 inches times 3 inches. And D is going to be the 4.5 inches minus the 2.303 inches that we calculated before. Because all that I want is this distance here. So I go from here to here, then subtract here to here. So that'll be 4.5 inches minus 2.303 inches. And don't forget the squared term. Then plus all of the contributions from the bottom piece. So that'll be 1/12. The base is 8.21 inches. The height is 3 inches, and so that's cubed, plus the area, which is 8.21 inches, times the height, which is 3 inches, times the distance between these would be this distance right here would be 2.303 minus 1.5. And that'll also be squared. Add all 4 of these terms together, and we should get 84.67 inches to the 4th. All right, so we've got the moment of inertia now. So now I need to start calculating the stresses. And so one thing, I wouldn't say that I missed it here, but one thing that you do want to keep in mind is that when you're calculating stresses for transformed sections, you might also need to multiply times the modular ratio. And I'm just going to put on like a sometimes. If you're calculating the stress in a portion of the cross section that has been transformed, you need to multiply times n again. And let's kind of see what that means. So here, let's do this calculation here. So if I want to calculate the maximum stress in the aluminum, like the stress up here at the top, I need to know this Y value right here. And here we're just talking about magnitude, so I'm not really going to worry about the negative value there, because if it was positive or negative, the magnitude is really all that we care about. So I'm just going to say that equals the moment about the z-axis, which we calculated earlier as 337.5 times w, times this distance right here, which is the full 6 inches minus 2.303. So 6 inches minus 2.303 divided by the moment of inertia, which is 84.67 inches to the fourth. And we know now that the maximum stress in the aluminum is given as 15 KSI. So I'll plug this in as well too, 15 KSI. So with a little bit of rearranging here, I should be able to calculate what W is equal to. So 15 times 84.67 divided by 337.5 divided by 6 minus 2.303. And I should get an W max of 1.02. And the tricky thing here with the units is that we converted the moment into kip inches, but W we kept as units of kips per foot. So this is 1.02 kips per foot. You could have left everything in kips and feet if you wanted to, or you could have calculated this in kips per inch. That just would have been 1/12 this 1.02 value. Completely up to you. It was kind of an odd choice with the units that I took, but it works out as long as you can keep track of it. And so this is what the distributed magnitude is going to be right when the aluminum reaches its allowable limit. And that might happen before the steel reaches its allowable limit, but we need to actually do the math to figure that out. And so I'm going to calculate the stress at the bottom down here by calculating the normal stress in the steel as equal to the moment, which is the same 337.5 times W, and its distance is just the Y bar value. From the neutral axis down to the bottom of the cross section is 2.303 inches, and the moment of inertia is the same, 84.67 inches to the fourth. So again, we're trying to calculate W. I know the allowable limit of the steel is 22 KSI. So same exact process, I rearrange it a little bit. I solve for what the maximum distributed load intensity is in the steel, and I get 0.875 kip per foot. So this is the steel, this is the aluminum, and this simply tells me the steel is going to fail before the aluminum, or the steel is going to reach its allowable limit before the aluminum reaches its allowable limit, because the maximum load based off the steel's limitation is lower than the maximum load based off of the aluminum's limitation. So this ends up being the controlling distributed load for the beam.